So we are very happy today to have our friend Helge Holden from Norway directly arriving without plane. And so the discussion will be difficult, but nevertheless, it will be better than nothing. And we will be very happy to have him speak about the Hunter-Saxton equation with noise. Helge.
Thank you very much, Eva, and thank you very much for the invitation. Of course, I feel very sad that I could not come to Paris. I mean, it's quite different from being in Paris from sitting in my office at the university here in Trondheim. But that's the way it is, and we've all been lecturing digitally this semester, but this is the first time I try with an international seminar of this type, so we'll see how it goes. So what I will talk about is Hunter-Saxton equation with noise, and that's a recent result that I've obtained together with Kenneth Carlson from Oslo and a very clever postdoc, Peter Pang from Trondheim. And we put the paper on the archive, so you can have a look at it there. So let me display the Hunter equation. Here's what it looks like. It's modest looking, innocent looking, nonlinear PD on the line. And apart from the overall derivative on the left-hand side, it looks like the Burger's equation with the source term. And we're going to look at the Cauchy problem, so we are given some initial data. And this was derived by Hunter and Saxton in 1991 in the context of liquid crystals. So they were playing around with models in several dimensions and simplifying to one dimension, and this was the simplest model they could get. And they studied some of the properties of it, and also some other equations that I will come to later. The first thorough mathematical study of the equation was given by Hunter together with Yuxit Zheng in '95 in 2 papers in ARMA, 2 thick papers where they systematically studied the equation and gave some of the fundamental properties. We will focus on the Cauchy problem, but it's also completely integrable. It has soliton-like solutions. It has some explicit solution like you can find for some of these equations. So it has very many nice features and has been studied a lot. Because of the derivative on the left-hand side, it's common to integrate it. And then, of course, you have various ways to integrate it. You can integrate from 0 to x. You can integrate it in the way that I displayed here in the sort of a symmetric fashion, which is kind of more common. And then you really see Burger's equation on the left-hand side with a non-local, non-linear, and difficult source on the right-hand side. So we will focus on the Cauchy problem, and we will focus on the existence, and we will add noise to the equation. So that's the topic of today's talk. So why do you study this equation? There are many other equations. It looks simple. What's the problem? The problem you can see from this formula here, and the I is the characteristic function. So if you look at this from the left, it's negative constant. Then is a linear interpolation on a small interval around the origin, and then it's a positive constant to the right. And this is set up in a way so that it's a continuous function, mostly constant, but then a linear increase. But you can see that the interval on which it couples the 2 linear states, it's getting smaller and smaller as t approaches 0. And as t becomes 0, it is 0. So here is a display of the equation. You can see, if you can see my cursor, this here is t equal to 0. I mean, it says t equal to 2 here, but that's a mistake. So this is t equal to 0. It's equal to 0. Then for negative t, it's this linear interpolation here, and here is positive t. So, and if you compare this to another function v, that is identically equal to 0. Then the 2 functions u and v share the following properties. They are equal at t equal to 0, and they are both solutions of the Hunter-Saxton equation. So this means that the uniqueness of this of the solution cannot be true, and you are stuck with this dichotomy between 2 solutions, and you have to resolve this issue. So, and this is a problem that will face us all through the analysis, that the uniqueness is a tricky issue. But you see that the solution is continuous. It interpolates like this. And you can see that as you approach 0, the jump becomes smaller and smaller, but steeper and steeper. And on the other side, it becomes, first it's very steep and then becomes less and less steep as t increases. So if we focus what happens around this wave breaking and loss of uniqueness, we see that we have the spatial derivative goes to negative infinity as t approaches some finite value. And at this point, you have, as I said, the gradient becomes unbounded. The solution remains continuous. So then we see that we are quite different from what it is in hyperbolic conservation laws. There is a loss of uniqueness that we have to resolve. And there are several ways to continue past wave breaking. We saw the non-trivial solution, but we also saw the 0 solution. So you can see this is illustration from the last slide. At this point t equal to 0, you can continue with 0. Nothing is wrong with that, but you can also continue with this non-trivial solution. I mean, it's hard to say which one is the correct one. So there are two prominent choices for this for the solution past breakdown, and that's a conservative, and the yellowish solution is a conservative, and the dissipative, where you just continue with 0, is that's a dissipative solution. So these two are extreme cases, but once it goes bad in such a way, it can go bad in many other ways. So it's not clear that there are only two solutions here. So I take a third and final look at what happens exactly at breakdown. So I will use Q as a notation for the spatial derivative. And I will look at what we call a box initial data. So it's constant on the unit interval equal to minus V0, and apart from that is 0. And then the solution can be computed. It is like this. And if we illustrate it, I've stolen this illustration from the original paper by Hunter and Zeng. We see that the box becomes deeper and more narrow, and it approaches minus infinity on an interval of length 0. And if we go past it, it comes up at plus infinity, and then it decays nicely. So this is a conservative solution, but at this point you could also just finish with continue with 0. So this is the problem that we are facing, and we have to resolve this this thing here and add noise. But let me, before I come to the equation with noise, let me mention two other equations. So there are two equations that are closely related to the Hunter-Saxton. It's a nonlinear variational wave equation, which is this second order equation where half the speed, so the c here, comes outside the derivative, and that changes the game, of course. And the c is bounded away from 0. And then you have the Kamasa-Holm equation, which looks like, it's not a pretty equation, but that's the way it looks at the bottom here. And these three equations, Hunter-Saxton, Kamasa-Holm, and nonlinear variational wave equation, are intimately related. Hunter-Saxton is by far the simplest, Kamasa-Holm is one step up, and the nonlinear variational wave equation is considerably harder. And they may look esoteric, these equations, but if you check on MathSciNet, which I did, you find 162 papers on Hunter-Saxton, you find 1,400 papers on Kamasa-Holm, and 1,300 papers on nonlinear variational wave equation. I'm not totally sure about the last one because the nonlinear variational wave equation could also be a name used for other equations that are not identical to the one here, but Kamasa-Holm is Kamasa-Holm, Hunter-Saxton is Hunter-Saxton. So, I mean, these equations look rather special, but they have been thoroughly studied. Okay, so let's review some of the previous work on the Hunter-Saxton. In addition to the papers I mentioned on my second slide, it's a paper by Zhang and Zeng. They have a series of papers, existing solutions, various properties, and they relate it to Kamasa-Holm and the nonlinear variational wave equation. Then you have some papers by Dafermos and Bresson-Constantin, and they studied the Cauchy problem globally for this equation. And then a paper by Beal, Sattinger, and Smiguelski, and they studied the inverse scattering for this equation. Closer to what we will study today, but not directly related, is the question of Lipschitz metric that addresses the question of uniqueness of this solution. Namely, if you could find a metric that has this property, so you compare two solutions with the two initial data at t equal to 0. If you have an inequality of this type, that would immediately give uniqueness. But this means that the metric would have to identify and distinguish between conservative and dissipative solutions. And the problem is that, of course, as you could expect, the usual norms, Lebesgue, Sobolev, they do not fit the bill. They simply do not work. So you have to construct and cook up metrics that select at the wave breaking the right solution. And this is tricky. And together with Bresson and Xavier Renaud, I studied this, and then more recently with Jose Carrillo and Karin Grunert, we gave a different derivation of a Lipschitz metric. And again, you have to be rather careful at the wave breaking. Okay, so I've talked a little too much about other equations. So now comes to the noisy equation. So here it is. And as I said, Q is the spatial derivative of U. So we added the noise term in red here. So, and of course, W is the Brown motion on the probability space, and sigma is a given function of space. And we will add more assumptions later. Essentially, it will be linear for reasons that will become clear later on. And circ is the Stratonovich product. So this is the equation that we will spend the rest of the lecture on. And we, as I said, we want to study the Cauchy problem with initial data in L1, L2. And there are two papers on Hunter-Saxton with noise, but they add the noise in a different way, and then the analysis becomes quite different. So I will not comment on this, but I just want to mention that there are other papers on this. So why do we pick this way? I mean, there is a certain arbitrariness in how you put the noise term into the equation. And we base this on a Hamiltonian approach. So you can derive Hunter-Saxton from the Hamiltonian like this, where this is the Hamiltonian. And if we modify the Hamiltonian by adding this term here, this noise term, which when it comes to the Hamiltonian looks like a natural choice, then you get the equation that we have. And if we introduce a Lagrangian like this, and from that the Euler-Lagrange equation, and we pick this Lagrangian where the black is the deterministic and the red is the noisy term, this term here, again we get the same Hunter-Saxton equation that we're going to study. So this is how we ended up with this, but in some sense there is a certain arbitrariness in how you add the noise term, and the analysis will be different depending on how you do it. Okay, so we will, for obvious reasons, study weak solutions. So let me just display here what I mean by that. So we have initial data in L1, L2. From the Q naught, we can get the U naught by just integrating. And this is, of course, the clear weak solution here with the initial and final time. And this is the double integral, and this is stochastic term. And we also have the relation between Q and U. And Q should be in these two spaces. It should be essentially L2 function of all variables. And there should be a certain regularity when it comes to the time variation. compared to, well, measured in L2 spaces. And I forgot to write down where the test functions are, but they are in the usual space. So these are the weak solutions. But of course, weak solutions will never give you a unique solution, but it's the first step. When you're playing with this stochastic equation, you always go back and forth between Stratonovich and Ito, and this is how the equation looks in Ito. So we get a lot of diffusion in the Ito formulation here. We get this term here with diffusion. Right, and then there is just a small calculation showing that weak solution in Stratonovich and Ito form are the same, which you hope and expect. So we need to approach the problem, the real problem, namely to distinguish conservative and weak solutions. We need to approach that problem. So a conservative solution should conserve energy, and the energy computed in terms of this is ux, q is ux and ux squared, and this is the time evolution of the energy density. Then you get this term, which is on conservative form, and then you get lots of terms here. And you see all of these terms come from the noise. So, I mean, if you drop the noise, that means essentially putting sigma equal to 0. All terms on the right-hand side, all these terms up to and including this term will vanish. And then it becomes a very simple equation to study. But we are stuck with all the other terms, so the analysis becomes not marginally more complicated, but more complicated. And this should hold in the sense of distributions, almost surely. Right, and so what do we do with the dissipative solutions? There are various ways to introduce a mechanism to select between the two. So this is the mechanism that we choose, namely that the weak solution should be such that ux, so which is q, should be bounded from above. So that's this estimate here, but it should be bounded on compacts. The constant may depend on the compact set, and also may depend on the realization. So this is an almost surely statement. So if you see, it looks kind of strange that you have this one-sided bound, but if you look at this illustration I had from the beginning, you see that the gradient here becomes negative infinity here. On the other side, where the conservative solution comes out, it's positive infinity. That's excluded by this fact that the derivative can't be positive infinity, but it can be negative infinity. So when you approach this point here, you have to continue with something without a positive infinity derivative. So this way you have to continue with the 0. And if you do the same calculation, it will not satisfy equality, but an inequality concerning the energy. So it may drop, or will drop. So that's the mechanism we have to distinguish between conservative and dissipative solutions. So the theorem that we're after is the following. So there does exist conservative and dissipative weak solution to the stochastic Hunter-Saxton with initial data in L1, L2, assuming sigma is linear. And so I'll show you where this linearity of the sigma comes into the game. I mean, we somehow had hoped for more, but right now we have to restrict ourselves to linear sigma, and it's not clear that that result will be the same in a more general case. At least the formulas will be much more complicated. Okay, so let's see. So we have some estimates with noise that are quite nice, and it takes some effort to get them. So if you have a conservative or dissipative weak solution, and this is in the general case where sigma is satisfying these conditions, then we have this estimate in expectation. So we can bound the L2 norm in space uniformly over T when we do the expectation first, like this. We can bound them in terms of the L2 norm initially. We can also do L2 plus alpha, and alpha is between 0 and 1. when we integrate over space and time in expectation. And these, they don't come for free, but they are nice because they compare very well with the deterministic estimates of Zhang and Zeng, because they are identical, except that because they don't have an expectation, because they are not noisy. So I mean, it's worthwhile to mention here, or any point at any time during the lecture, namely that we are selecting the conservative and dissipative weak solutions. We are not excluding that there are others. And in fact, there will be others that are sort of in between conservative and dissipative, but they are not covered by our analysis, because that goes for the sort of the extreme cases, either conservative or dissipative. Okay, so let's specify then to the conservative case. We obtain this very nice formula that if you look at the L2 norm of the energy, so remember Q is Ux, and this is in the linear case, we get a nice formula for how it develops in time. It's modified by an exponential where the Brownian motion sits in the exponent. And remember that sigma prime, because sigma is linear, sigma prime is a constant. So this is a constant term in the exponent multiplying the Brownian motion. And so it is a very nice formula. And if the derivative is equal to 0, then indeed you have true energy conservation. But this is sigma prime that is equal to 0. It's not sigma itself. So if you add noise with a constant sigma, but still there is Q sitting there, is noise sitting there, then the energy will also be conserved. So if you have a noisy solution where energy is conserved, but when sigma is truly linear, you will have this relationship, which is quite nice. If you assume that the initial data is deterministic, we can very precisely see how the energy develops. So energy is pumped into the system. I mean, the noise term gives energy into the system, and we can specify exactly how it goes. It's given by this term here. So now I approach the construction of the solution and how we obtain this theorem. So then we will formulate this in Lagrangian coordinates. It's different from the Lagrangian equation. Maybe this was not a good term. So we do some formula manipulation to see how we can get, and then where we can get, and then we try to construct the solution afterwards. So this is the equation, and we assume we have a solution. Then the characteristics will satisfy this equation. And you see, this is another argument why we think that this is a natural way to add the noise to the Hunter-Saxton. We take the characteristics, which are given by the first part of this equation, and we add the noisy term to the characteristics. And that's what gives us our equation. Okay, so here comes the key computation. So if we look at this quantity, which it's supposed to be a big Q, so I call it frac Q, and this is Q along the characteristics. And this satisfies, and this is a straightforward calculation, it satisfies the stochastic Verhulst equation, which is given down here. Okay, so, and of course we don't have the characteristics yet, and the characteristics are sitting inside here. We don't have the solution as well. So this is the Verhulst equation, but it so happens that this can be solved. This has a solution, and it's given by Holden and Platen in their book by this expression here. And this is in the case where sigma is linear. I mean, there is also an expression for this in the general case for a general sigma. But you see, and here's where we are forced to take sigma linear. because sigma linear gives this as a number. This does not any longer depend on the equation. And this means that the right-hand side is explicitly known. This means that frac Q is explicitly known. And remember that frac Q is Q along the characteristic. We neither know Q nor the characteristic, but we know their composition. And that's given by frac Q. And this is the starting point. And it also gives a very nice formula for when you have wave breaking in the random case, because this is not at all clear once you add the stochastic term. It is clear in the deterministic case, but it's not at all clear in the stochastic case. But this formula reveals that when the denominator becomes 0, then you have the wave breaking, because this is QX, the QA or UX. And wave breaking happens exactly when this term is equal to 0. So we have an equation for the time of wave breaking depending on the x. And you also see that if Q naught is positive, the left-hand side is positive, so there cannot be any wave breaking. But if Q naught is negative at any point, you will eventually have wave breaking. So it's very easy dichotomy between wave breaking and non-wave breaking, namely the sign of Q naught initially. So it's very nice that we have this formula. Okay, so let me continue with the construction of the conservative solution. So we have this frac big Q, then we construct frac U as this thing here, and this can be computed explicitly, and we know this. And why do we do this? That will become clear at the bottom of this slide. And then we compute big psi as the integral of frac U. And now comes the equation. Now we can suddenly find the characteristics, because the characteristics are given by the integral from 0 to t of big psi times this, the stochastic integral here. But this, since big psi is now a known function, this equation can be solved for the characteristics. And if you remember the definition of the characteristics, this should be the U composed with the characteristics. But we don't know the U, so we can't use the U inside here. But the composition of U with the characteristics we can compute, and that's called big psi. So that's the trick behind this calculation on the slide here. So now we can compute the characteristics, and we can indeed compute Q, and from the Q we can compute the U by integrating. So little q, which is UX, is frac Q, where the spatial arguments here, X and Y, are connected using the characteristics. And the characteristics are given by this. So the fact that we could solve for the frac Q explicitly was the starting point for resolving all these problems with to identify the characteristics. Okay. Right. And then comes we can also analyze the breaking times. Now we have an equation for them. So if you look at this T star X, they are the breaking times in the linear case, and we define this quantity. We can compute the distribution of breaking points. So the probability that the breaking times exceed a certain time t is given explicitly by the probability of this set here, which can be computed. And again, you see that if Q naught is positive, then the right-hand side is negative, and this inequality can never be fulfilled. So it's an empty set, probability being 0. So again, I mean, if Q is positive, there will be no wave breaking. But as soon as Q naught is negative, this becomes positive, and you can compute this. So we have this nice distribution of the breaking times. So then we turn to the dissipative solutions. So how can we mimic the construction we did in the conservative case in the dissipative case? So we take this frac big Q that we had computed, and we modify it by the indicator function. So that past wave breaking, we just put this equal to 0. It looks a little bit abrupt, because remember that wave breaking can take place at the isolated point in space and time, and the solution away from this point of wave breaking should continue uninterrupted. But here it seems that we are just putting it bluntly to 0. That's because this frac Q is Q along a characteristic. So we are sitting on this particular characteristic, and then we have to turn it off. We do the frac little u, and it's given as before by this expression with the new Q. And if we do the computation, it comes out nicely with the same expression, except that we again modify with an indicator function. If we do the big psi, and we do the characteristics, the equation for the characteristics. So this means in plain words that when you have wave breaking, this means that characteristics come together. And once they come together in the dissipative case, they remain together. They are not going apart as they would in the conservative case. They just remain together. And all the characteristics that are trapped between the two extreme ones are being merged into one characteristic. So this equation is different because the psi is different from what it was. And again, to recover the Q, that is solution, it's equal to the big Q along the with the spatial point connected using the characteristics, and that is the dissipative solution. So in the dissipative case, of course, we cannot have energy conservation. Well, we didn't have it in the conservative case as well because energy was pumped into the system. Here in the case of sigma being linear, we have the L2 norm of Q given on the left-hand side, which in the conservative case with no noise is conserved. In the dissipative case with noise, you have the initial data here, multiplied by this exponential term and the characteristics. So this will turn off at certain points along the real line where they have wave breaking. So then energy will be abruptly removed from the system. So then comes some work that is in progress. We don't have all the details yet, and we hope we will have them. So this has to be taken with some skepticism. So if we look at the energy as mentioned in the L2 norm, I mean, I said that I'm not saying that you only have two possible solutions of the Hunter-Saxton equation. You may have infinitely many between the two extreme cases, the conservative and the dissipative. So you can ask yourself if a solution is maximal dissipative, if the drop is the highest in energy. So no other sort of weak solution has lost more energy. That's a maximal dissipative solution. And a natural claim is that, well, the maximal dissipative solution is what we call the dissipative solution. So that is a claim. And in the case sigma is linear, we hope that we can prove this. This is still work in progress. It would be surprising if this result is not true. It doesn't mean that it is true and it has to be proven, but that's what we expect. And this is solidly supported by results in the deterministic case by the Fermos and Cislak and Yamarosh, and both of them, both groups here have very solid arguments for and intricate arguments for why this is true in the deterministic case. So, and we think we can prove it also in the stochastic case. But it's, as I said, it's still work that needs to be done. So I was a little bit hesitant whether I should add these to the two slides coming up here. And this may not be of interest to all, but it's if you have already had or will have a look at the paper of Zhang and Zeng, where they do a very nice analysis in the deterministic case. They show a uniqueness and stability and all sorts of things in the deterministic case. They use a completely different approach than what we have used here. So I just want to review this and comment a little bit on it. So what they do is that they give an initial data and introduce a partition on a finite interval on the real axis, and they do a piecewise constant approximation of ux, right, or q. So that's this thing here. Q initially is a piecewise constant on these intervals, like that, and they take the average value on this interval. Then you integrate. This is essentially an interpolation. You use this initial data and you integrate it. I'm not giving all the details on this slide, but it's basically going from Q to U, you integrate. So this is a linear interpolation that you're given here. And this is the function, and you recognize this as the solution of this Verhulst equation. Now, the characteristics you cannot really compute explicitly unless you're rather careful. So the way you do it is that you compute it from left to right. So I start with x naught, which is a point to the very left, and then I can compute the characteristics like this. Knowing this characteristic, I can compute the next characteristic at going out of x1 by using the previous one plus a correction term. And this I can do, and that's covered in the innocent looking, etc. Because this becomes more and more complicated as I proceed to the endpoint xn. I compute these characteristics. And then I have my UP, which is a sum of these linear interpolations, and I have my Q, which I can solve explicitly. Because they are coming from this box initial data, and I can compute them between two characteristics. And I've given here the dissipative case, so it's turned off as soon as this condition is not satisfied. So then you may consider this and take the partition to 0 or to infinity. I don't know. You make it finer and finer, and then look at the limit. And that's what Zhang and Zeng do in their paper. And now I've written down the corresponding formulas in the stochastic case. And this is, it's reasonable to expect convergence, but also in this stochastic case. But I don't know if how easy it is to get the nice formulas that we had for the conservation of energy and the distribution of breaking times, because if you take the limit here, you will sort of lose control on the limits. So we decided to follow this different approach that I just described. But this is for the people who have looked at the very nice papers of Zhang and Zeng on the Hunter-Saxton. Okay, so we're approaching the end here with the summary. And so what we have studied is the Hunter-Saxton equation with noise added in this way here. We have derived this way of adding the noise term from Hamiltonian or Lagrangian principle. We have also seen how it looks fairly natural when you look at the Lagrangian reformulation of the equation. It's just adding this random term to the equation for the characteristics. And we have shown how to prove that there exist conservative and dissipative weak solutions to this equation, assuming that sigma is linear and the initial data are in L1, L2. And we have these two formulas for given the breaking times. We have how energy evolves over time. We have this term here, and this indicator function is in the dissipative case. In the conservative case, it's simply not there. And we have this probability or this probability distribution of the breaking times for the full equation. And that's it. So thank you very much.
Okay, thank you, Helge. Now we are going to the question part. So if you want to ask a question, raise your hand and I will give you the floor. So on my side, I have already one question. So you said that the problem comes from the model of the nematic crystal.
Yes.
And that the noise part comes from the Hamiltonian. The Hamiltonian is based on physical reason. It is still related to the nematic crystal, and if yes, what kind of effect does it is it related to?
Well, that's a tricky question. I'm not sure I really can answer it fully, but I mean, in the paper by Hunter-Saxton, they introduce the Hamiltonian in this way. So they derive it in this context of Hamiltonian formalism. When we add the stochastic term, that is something we do by our own, on our own. I mean, we have no physical justification for it as such. So that's the sad but simple answer to it.
Okay. And so on the same way, so you take sigma linear and you explain why sigma linear is important at some point when you take the derivative. But so do you think it would be interesting to go further and try to have a different expression for the sigma?
Yeah, I mean, I have to confess that we were a little bit disappointed that we were forced to do sigma linear. But there are some interesting consequences of this in the sense that we got some indication that maybe this is a physically relevant case, because there are other formulations of the stochastic Kamasa-Holm and related equation by Holm and collaborators, and if we follow their approach, we need sigma linear. So maybe there are some reasons that we have not understood why sigma linear is necessary. But I mean, mathematically, you feel a little bit deprived when you are forced to do linear sigma, right? I mean, the equation is non-linear, but why linear sigma?
Yeah, that was the point. Benoit, you have a question?
Yes, Helge, thank you for your talk.
Hi.
And I'm curious to know if there are people who have been trying to do white noise in space and time, not only time, with higher methods.
No, I think the answer is no. No, we have not, and I don't think anyone else has tried. I mean, that is, of course, a very natural and interesting question.
Does it make sense? Is there any chance that there is something occurring when you make numerical simulations?
I mean, one thing that we have not tried, which we should try, is to do simulations, you know, pushing the limit, say taking nonlinear sigmas, add the noise in different places, and play on the border of what we can actually prove, but we have not. So that would be interesting, but I mean, the techniques would have to be different, I think.
Yeah. Okay, thank you.
Other question? Maybe in the so I have not completely understood the notion of characteristic. So for me, characteristic is something where you preserve, and it went too fast for me to see if there is some classical understanding of the notion of characteristic in what you have proposed.
Well, I mean, if you drop the noise term, it will be the characteristics that we all know, right? But in some sense, the characteristics is sort of on the right-hand side. You have the U, the unknown, right? And you have the X. So you need to find one before you can do the other. So yeah, so I mean, the characteristics are just the regular ones, and you perturb them in a random way, in a natural random way. And the problem is that you suddenly have you have the U and you have the X, and you don't know either of them. So it's not so easy to get a handle on this. What is interesting that came as a surprise was that if you add constant noise, not linear, constant noise, but there's noise, then the characteristics will wiggle, but everything will be sort of the same. Energy is conserved, but characteristic will just wiggle, which is kind of strange. So you make a transformation on your x-axis, and then suddenly a random, you move your origin, and then it will look the same. It's kind of strange. So to add a little bit noise, the changes, you're just looking at this with a blurred vision.
Okay, so instead of going straight, there will be wiggles in the...
Yeah, there will be wiggles, yes. Yeah.
Okay, interesting, okay. Benoit, you have another question?
You mentioned this contraction in a Lipschitz distance. Do you mean real Lipschitz or the dual Lipschitz? Moshkantorovich? What is the D you were putting in your slide?
Yeah, this requires a separate talk, Benoit. This is it's a difficult thing. It is, I mean, the way we derived it recently, this paper I think was out early this year or late last year, was we do cont'd, which we do, yes, so we follow this approach, but the computation is disappointingly complicated. And it is rather delicate because I mean, as you can see from the behavior at the wave breaking, you have to be very careful how you select your continuation. I mean, what you basically do is you change the equation into variables where there are no singularities. These new variables then have to accommodate whether you are sitting on conservative, dissipative, or something strange in between.
Wow.
So you have to, and that's how you do it, and that's why these equations are related. There is some sort of a transformation of the equation into Lagrangian-like coordinates where the singularities just disappear. And then you have to measure distance in these new variables and translate that into distance in the old original variables. And that's a careful thing. That's delicate. But that's a topic of a separate talk because it's such a long, this is such a messy thing.
And also another question: is there any higher dimension version of it, or it's Hunter-Saxton can only be done in 1D?
Hunter-Saxton, I'm not totally sure. For Holden, they are higher dimensional, and variation of wave equation, they're higher dimension. Hunter-Saxton, I'm not totally sure. But certainly for the others, they are.
Okay. No more question. So everything was clear. So thank you, Helge, again.
Thank you very much to all of you for listening. I appreciate this.